Hello everyone and welcome back. I'm going to be looking at some more organic chemistry today, and this video is going to kind of act as a sequel to my previous video on organic chemistry. In the first video, it was really an introduction to the basics of hydrocarbons, and so that would be how to name and also draw different organic compounds. This video is going to focus on different groups that we can see attached to hydrocarbons, and we are going to be looking at ring structures as well as oxygen chains. Let's start with ring structures, and they are pretty self-explanatory. A ring structure is when we have a hydrocarbon chain that has kind of folded onto itself and it's formed a closed loop. So this is going to appear like a regular shape. We've got a triangle, a square, and a hexagon in front of us. And luckily for us, we can count the number of carbons in these hydrocarbon chains, just like we would any regular organic compound. So that means we're going to be looking at the ends or the vertices of our shape. So here for my triangle, we've got 1, 2, 3 carbons. So if this were a regular hydrocarbon chain, we could call this propane because we use the prop ending to signify 3 carbons. However, we do need to name ring structures a little differently than regular hydrocarbons. And what we need to do is add the cyclo prefix. So this is going to be called cyclopropane. And that's all there is to that one. Let's take a look at the square. We've got 1, 2, 3, 4 carbons. Normally this would be butane. All we got to do is add cyclo. So we've got cyclobutane. And finally, with a hexagon, we have 6 carbons. So this would be cyclohexane. Now, things get a little bit more complicated when we have different functional groups attached to our main ring structure. And just like for a regular hydrocarbon, we're going to have to number and name these functional groups when we write out the complete name of our organic compound. We are going to start with the main ring structure. So I can see here that I have a 5-carbon ring. So we've got cyclopentane. So I could right away just write that down here. But now I need to think about all of the different things that are attached to our cyclopentane. We have a bromine here. We have an ethyl group here because it's 2 carbons. And we have a methyl group, which is just 1 carbon branching off. And what we need to do is try to make our numbers as low as possible. So I can tell that if I were to start counting from the bromine, this would be on carbon 1, the ethyl group would be on carbon 2, and our methyl group would be on carbon 3. And that's going to be the lowest numbering possible in this situation. Next, I need to write them out in alphabetical order. And luckily for us, it's already in alphabetical order because we have bromine, B, ethyl, E, methyl, M. So this is how we're going to write that out. 1 bromo, 2 ethyl, 3 methyl, cyclopentane. And that is so long, I didn't even have enough space to write the whole thing. But anyways, that's what the name would be. So there's a lot going on in the name, but again, all of it is following the usual rules of naming organic compounds. What happens when we have a really, really long carbon chain and we have a ring structure kind of shown as a branch on this carbon chain? So let's take a look at this example right here. I can see here that I have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon long chain. So we would call this a decane. And we have kind of a weird branch off group here. So that looks like cyclopropane, and it is cyclopropane, but because it's not considered the main structure of our chain, we have a decane, or technically a decene carbon chain because of the double bond here. Because we have way more carbons on our main chain, we're going to treat this as a branch. So we are going to have to number what carbon this branch is on. And we're also going to name it a little bit differently. So instead of cyclopropane, this will be a cyclopropyl group. So all we've done is added the cyclo prefix, and then just written the normal name as we would for any regular propane branch. So that would be a propyl group. If we were to look at the main carbon chain, we have a double bond on our second carbon. So we could say this is dec2ene, and we use the ene ending for the double bond, and we're specifying where that double bond is. And then we have our cyclopropyl group on our fourth carbon. So we'll write that at the beginning here. For cyclopropyl dec2ene. And that looks good. And so let's compare this to the type of question we did previously, where our main structure is the ring structure. So here we have a 4-carbon ring structure. So we have a cyclobutane. But we have these 2 methyl groups attached to a carbon. And obviously 4 carbons is greater than 1 carbon. So we would treat our ring structure as our main group or chain. And so we need to list these methyl groups as branches. The way we're going to do that is, since they're both attached to the same carbon, we're actually going to write where they are twice. So we're going to say that this is the first carbon to lower our numbering. And then we have 1,1-dimethyl, because we've got 2 of them, cyclobutane. And that would be correct. All right. Beyond the regular ring structures, we also have a special type of ring called benzene. And sometimes it may be referred to as an aromatic group, but its official name is benzene. And this is benzene right here. So you'll notice it very much looks like cyclohexane because we have 6 carbons in our closed ring structure. However, it includes alternating double bonds. So we've got 1 here, 1 here, and 1 here. And so when we see a hydrocarbon like this, we're going to be referring to it as benzene. That is when it's the main structure. So just like in this scenario up here, where we had the ring structure as our main chain, that's when we're going to call it benzene. However, if we have a scenario where our benzene is acting as a branch, because we have a larger carbon chain that it's attached to, we would call it a phenyl group. And so let's go through 2 examples that's going to highlight this difference. In our first example here, we are going to treat benzene as our main chain because it consists of 6 carbons, and all we have attached to it as branches are an iodine here, and then it looks like this is a propyl group here because we have 3 carbons. So we know that they're going to have the name benzene here. We just need to number our branches to have the lowest numbering possible. And that would happen if I say that this is our first carbon. And so therefore this would be our 3rd carbon. So we are already in alphabetical order. This is going to be 1 iodo, 3 propyl benzene. Okay, let's take a look at this one now. And if we were to count our carbons on this chain here, we've got 1, 2, 3, 4, 5, 6, 7, 8. So since we have 8 carbons, that is obviously larger than 6. So I'm going to treat this benzene here as a phenyl group and refer to it as a functional group that is branching off of our main 8-carbon chain. If we look here, we do have a double bond. So usually double bonds are going to get the priority in terms of naming. So we have a double bond starting on our 2nd carbon. Therefore, I would have to refer to the iodine being on the 4th carbon and our phenyl group being on the 5th carbon. So let's try and write this all out at once. I do need to put iodine first because of the alphabetical order rule. So we're going to say 4 iodo, 5 phenyl, oct, 2 ene. And this 2 right before the ene is just referring to where the double bond is. So that's all there is to that one. All right, that's enough for ring structures for right now. Let's move on to some oxygen groups. So a lot of students in organic chemistry get overwhelmed with the number of oxygen variants that you're going to see in organic compounds. So what I'm going to try and do is sort of walk you through all the different types that we have and their usual naming conventions. So when we see oxygen in an organic compound, that is going to give us a lot of key information in terms of what kind of compound we are dealing with. Let's ignore everything except for right here. Let's look at the alcohols first. So I have 1, 2, 3 carbons here, and there is an oxygen attached to the end with a hydrogen attached to that oxygen. So we could call this hydroxide, or we could just say it's a hydroxyl group. And whenever I see this, a oxygen with a single bond to a carbon and then a hydrogen bonded to that oxygen, that's when I know I have an alcohol. So the naming conventions for alcohols, we are just going to use the OL suffix and attach it to the main carbon chain that we're dealing with. So we have 3 carbons, that would be a propane, but because we need to reference the fact that it's an alcohol, we're going to call it propanol. There are cases where our hydroxyl group is not at the terminal end of our hydrocarbon chain. So as you can see here, the oxygen is at the end of our chain. But if I look down here, there can be situations where this hydroxyl group shows up in the middle of the chain. When this happens, we always need to give the numbering priority to our hydroxyl group. So no matter what's going on, whether we have double or triple bonds, the hydroxyl group is actually going to take priority. So let's figure out what our main chain is here. We have 1, 2, 3, 4 carbons. And then we have a hydroxyl group on our 2nd carbon, and then a methyl group on our 3rd carbon. And the way we're going to write out this name is we're going to say 3-methyl butan 2-ol. So this we've already dealt with. We're just specifying where a branch is. This is the suffix we're using to represent the fact that we have an alcohol. And the 2 is referencing where our hydroxyl group actually is. Okay, that takes care of alcohols. Let's move on to aldehydes. What's the difference between an alcohol and an aldehyde? Literally, the only difference is we've gotten rid of our hydrogen bond on the oxygen, and instead we've added a double bond between a terminal carbon and our oxygen. So aldehydes are special because the oxygen is always going to be at the end of the carbon, or I guess, depending on how you look at it, the beginning of the carbon. So we don't actually have to worry about numbering where it is when we name it. When we're dealing with an aldehyde, instead of the OL ending, it's just going to be an AL ending. So going from alcohol to aldehyde, not too much to do. If I were to count my carbons, I'm going to go 1, 2, 3, 4, 5. So this would just be pentanal. So not pentane, not pentanol as an alcohol, but pentanal because of the double bond. Just like alcohols, this double bonded oxygen may appear in the middle of our main carbon chain. Now, I just said that for aldehydes, that doesn't happen because we are at a terminal carbon. So if we see a double bonded oxygen in the middle of a carbon chain, that must mean we're dealing with a different kind of organic compound, and this would be called a ketone. So for ketones, we are going to have to specify where the oxygen is, and we're going to do that using the normal naming conventions, but then just using the ending O-N-E. If we were to look at our main chain here, we've got 6 carbons, and if I counted from right to left, that would give me the lowest number of a 3 here. So we could say that this is hexan 3-ome. So we're saying hexan for hexane because we have a 6-carbon chain, and then we're specifying where our double bonded oxygen is. As I mentioned in the first video, it is common to see the numbering for the main oxygen group that we're dealing with at the beginning of the name. So you could see it written like this, 3-hexanone. However, I personally prefer to put the number right before the suffix, just to show that they are directly connected. Okay, we've done alcohols, we've done aldehydes, we've done ketones. What about these nasty looking things? Carboxylic acids. So a carboxylic acid is kind of like if we put together an alcohol and an aldehyde. We can see here that we have the hydroxyl group from alcohol, but then attached to the same carbon, we also have a double bonded oxygen. And I think I forgot to mention that this double bonded oxygen is called a carbonyl group. So when we have both of these groups attached to a carbon, and this is always going to be a terminal carbon, we have a carboxylic acid. Thankfully for us, the naming isn't too bad. All we need to do is add the suffix, oic acid. So let's see how many carbons we have on the main chain. We've got 4, and then we have our carbonyl group and our hydroxyl group. So this is going to be called butanoic acid. However, things can get more complicated when we add different branches onto our carboxylic acid, just like with any other organic compound. So here, we still need to use the oic acid ending because I have my carbonyl and hydroxyl group here. And then I just need to make sure I'm counting the right number of carbons for my main chain. If I start on the carboxylic acid side of things, because that's going to get priority in the numbering, we have 1, 2, 3, 4, 5, 6 carbons. And then we have a bromine here and a methyl group here. So sometimes these more complicated looking compounds are actually easier to name because we know we need to start counting our carbons from the carboxylic side of things where we have the hydroxyl and carbonyl groups. Therefore, our bromine is on our 3rd carbon and our methyl group is on our 4th carbon. So this would be 3 bromo 4 methyl hexanoic acid. All right, we are almost done. However, there are 2 more oxygen groups that I want to look at. We've dealt with an oxygen and hydrogen together. We've dealt with a double bonded oxygen in the middle of a carbon chain, and those 2 groups bunched together for a carboxylic acid. Sometimes we're just going to have a lone oxygen in the middle of our carbon chain. And when that happens, we have what's called an ether. So it's just going to be an oxygen single bonded to 2 other carbons. And all we need to do is identify what the longer carbon chain is between these 2 branches. So I've got 3 carbons on the left, 4 carbons on the right. So therefore, this side is going to be our main chain. So we're just going to use the regular name. This would be a butane. What we need to do is mention where the other or secondary carbon chain is. We know it's branching off of the oxygen. So if I say propoxybutane, this part is specifying this chunk of the line diagram. Because we have a propyl group, or propane, for 3 carbons, and then we use the oxy ending to specify the fact that there's an oxygen at the end of that carbon chain. But it's actually attached to a larger carbon chain, which is the second part of our name. You may see this name written out as 1-propoxybutane, and that's fine too. That's just specifying the fact that the oxygen is bonded to the first carbon in our main chain. Okay, just one more to go. We have an ester. And the special thing about esters is they are actually created when we have an alcohol and a carboxylic acid joined together. So if I draw out an alcohol here and a carboxylic acid, what happens is we have 1 oxygen and 2 hydrogens coming together. Those elements are going to form water. And what we have left over is we have something that looks like this. So what we could actually do is we could think of an ester in 2 parts. We could look at the carboxylic acid side and we could look at the alcohol side. Because carboxylic acid has the double bonded oxygen, I'm going to treat this part of it, this part of the ester, as the carboxylic acid part of it, and then the side that only has the oxygen as the alcohol side. So this is carboxylic acid, this is alcohol. And that's important because the alcohol part of the ester actually needs to be written out first in its name. On the alcohol side of things, I have 5 carbons. So this is going to be a pentyl group that's attached to the carboxylic acid. So this would be pentyl propanoate. And this is the ending we're going to be using for the ester, an O8 ending. Pentyl refers to the alcohol, propanoate refers to the carboxylic acid. Okay, I know that was a lot, and thank you for watching all of that. The name of the game for this is really just practice. Practice drawing line diagrams, practice naming line diagrams. And the best way to do this, as I mentioned in my first video, is to go to chemquiz.com, or I guess it's .net. And so here you can actually create your own custom quiz on organic nomenclature. And since we've covered a lot, we can actually probably do most of what's written here. We can definitely talk about carbons that are in the 8 to 10 range. We focused on alkanes, alkenes, and alkynes in the first video, and we just got done with alcohols, aldehydes, carboxylic acids, esters, and ethers. And also ketones. We've actually done all of these. There are other functional groups, such as amines, that we haven't done, but we have done aromatics. So we pretty much covered everything on this website. And whenever you're ready to start, you can just create your own custom quiz and get to practicing. So I'll leave this for you to try on your own. Let's just try a couple before we wrap things up. And instead of getting the name from a line diagram, let's see if we can create the line diagram from the name, just to switch things up. The first example here, we have 2-methyl-4-pentanal. And when I'm given the name, I actually want to start at the end of the name, because this is going to tell me, A, what's the main carbon chain, and B, what kind of organic compound are we dealing with? Because I see the AL ending, I know we're dealing with an aldehyde. Therefore, I need to have 5 carbons where I have a double bond in oxygen at the end. Then I need to specify where this methyl group is. So it's on the second carbon, and we know that the carbonyl group is going to have priority. So our second carbon is actually here. So we just have 1 carbon branching off there. And we're actually not done yet. Because we have the EN ending, so pentene instead of pentane, there's actually a double bond going on here. And the name is specifying that it's happening on the 4th carbon. So that's going to be right here. So this is our 4th carbon, and it's going towards the left. All right, and I think I'm going to leave it there. So if you want to try the second example, you can for extra practice. But this video is long enough already. So that'll be it for today. Thank you very much for watching. Hopefully this was helpful. And good luck studying organic chemistry.